Hi everyone! In this video we're going to learn about inverse trigonometric functions. But let's start with refreshing 2 out of 3 words in this title: function and inverse. You learned these concepts in algebra, but it would be good to review them. Here's the definition of a function. Function is a relation in x and y such that for every x there is only one y. To better understand this definition, I like to think about a function as the box, with some values that go in the box and some values that come out of the box. And function relates these values. Based on what goes in the box, function determines what's going to come out of the box. And that's why it's common to call values that go in the function inputs and values that come out of the function outputs. So far, we have illustrated the first part of the definition. Function is the relation in x and y. But there's a second part that says that for every x, for every input, there's only one corresponding output. So if I keep feeding, let's say, 5 into the function several times, I would always get same output every time. And there are 2 important terms that come with a function. All possible inputs or possible values that we can put in the function are called the domain of the function, and all possible outputs are called the range of the function. Now let's look at an example. I'm going to show you a picture. It's called arrow diagram that illustrates a function. So values 5, 0, and -3 represent domain of the function. These are the inputs. And then values -2 and 7 represent the range of the function. And this is how a function relates these values. Input 5 produces output -2, input 0 produces output 7, and if I put -3 in the function box, -2 is going to come out. Let's name this function g. By the way, is there anything wrong with the fact that input 5 has output -2 and input -3 has output -2? Does that violate function definition? Well, no, because remember, by definition, each input can only have one corresponding output. So input 5, how many outputs does it have? Well, only one, it's -2. Input -3, how many corresponding outputs does that one have? Well, also just one, -2. So we are looking at a function. Each input has only one corresponding output. So it just happens that some inputs have the same value for an output. Here's another example. Domain is 5, 0, -3 again. Now range has values -2, 1, 7. And this is how the values are related. Let's call this function f. How is it different from function g? Obviously range has one extra value, but what else? Well, in function f, we don't have that situation where 2 inputs have same kind of output, right? In function f, each input has unique output. 5 goes to -2, 0 goes to 7, and -3 goes to 1. And for this reason, this function f, is called one-to-one function. And then you can guess that function g is not one-to-one. So a function is one-to-one if for every output, there's only one corresponding input, right? So for every output, for every value in the range, there's only one corresponding output for a one-to-one function, versus not one-to-one function where it can happen that output has more than one corresponding input. Why do we need to refresh one-to-one functions? Well, because every one-to-one function has an inverse. And as you remember the topic of this video, inverse trigonometric functions. So let's review inverse functions. What is an inverse function? The idea is actually pretty simple. If we take a one-to-one function and do the following, all the values that represent range of the one-to-one function, we're now going to call domain. And all values that represent a domain of the original function, we're going to call range. In other words, we switch inputs and outputs. -2, 1, 7 become inputs, and 5, 0, -3 become outputs. That defines an inverse function. And we usually call it by the same name as the original function. However, we put something that looks like power -1, but it's not a power. It's just the notation for the inverse function. We read this f inverse. So once again, -1 next to the function name is not a power. It's notation for the inverse function. Okay, so as you can see, the idea of the inverse is pretty easy. You just swap inputs and outputs and you get inverse function. Now, why is it only one-to-one function can have an inverse? If I look at function g, I have no problem switching arrows. I'll call -2 and 7 domain. I'm going to call 5, 0, -3 range, and I'll just reverse the arrows. I can easily do that. But what is the problem here? And the problem is that the relation I just created is not a function. Why is that? Well, as we just said, -2 and 7 are inputs, right? But what can I say about input -2? Well, I can see that input -2 has two corresponding outputs, right? 5 and -3. And that violates function definition. Because remember, relation is called a function if every input has only one corresponding output. And obviously, that's not the case here. And it's not the case because function g was not one-to-one. So now you can see why only one-to-one functions have inverses. And since our topic is inverse trigonometric functions, it would be logical to think that trigonometric functions have to be one-to-one so that we can obtain their inverses. But are they? Let's use cosine function to investigate that. Is it a one-to-one function? Let's check. Let's pick an input. For example, pi over 4. If pi over 4 goes in the box, what will come out of the box? Well, it's just plugging in pi over 4 into the cosine function and getting radical 2 over 2 as the output or outcome. Okay, but can we think about other inputs that produce same output, radical 2 over 2? Yes, we can. For example, 7 pi over 4. Cosine of 7 pi over 4 is also radical 2 over 2. And in fact, there are infinitely many other angles that terminate at the same place as pi over 4 and 7 pi over 4 that have exactly the same cosine value, radical 2 over 2. So, is the cosine function a one-to-one function? No, it's not. We just saw that same output has more than one corresponding input, and we can come up with other examples like that. So how come today's topic is inverse trigonometric functions? Well, we're going to do a certain trick. Yes, cosine function is not one-to-one. However, we can restrict the domain and make function one-to-one. So restricting domain means that we're going to say, well, you're not allowed to look everywhere you want for inputs. There's going to be only a certain interval on which you can take inputs for cosine function. And with that restriction, we will not be allowed to use 7 pi over 4 or anything actually more than pi or less than 0. Let's look at it a little bit closer. Each basic trigonometric function, cosine, sine, and tangent, is going to have domain restriction. So for each, we're going to pick only 2 quadrants that we're going to use for domain. And each function is going to be one-to-one over that restricted domain. So let me show how it works. For a cosine function, we're only going to pick quadrant 1 and 2, so these are the values from 0 to pi, and that's going to represent the restricted domain for the cosine function. So inputs that we're going to use are going to come only from the interval from 0 to pi, while including 0 and pi. Because think this way, no matter what angle you're going to pick from this interval, they're all going to have different cosine values. Well, in quadrant 1, they're going to have positive cosine values. In quadrant 2, they're going to have negative cosine values. But there are no 2 angles on this interval that have same cosine value. Well, that means that on this interval, cosine function is one-to-one, and that means that we can obtain its inverse. See how it works? Let's talk about the domain restriction for sine function. On which 2 quadrants, no 2 angles have same sine value. And the trick is also going to be similar. One quadrant has to have positive sine values, the other quadrant has to be negative sine values. Well, there are options here, right? We can use different combinations of quadrants. but it's common to use quadrants 1 and 4. In quadrant 1, sign values are positive. In quadrant 4, sign values are negative. However, we have to be very careful about the interval itself. The interval is going to be from negative pi over 2 to pi over 2. You probably already got used to the fact that on the unit circle down here, we have value 3 pi over 2, right? But think this way. Remember, when we describe interval around the unit circle, we always go counterclockwise, and we always have to go from smaller value to the larger value. And if we had 3 pi over 2 over here, it would not work, right? You cannot go from 270 to 90. Well, that's kind of going backwards. So for this reason, the right way to describe this interval is to start at negative pi over 2. Well, then you're going to pass 0, and then you reach pi over 2. But because of this kind of interval and this kind of domain restriction, you need to realize that angles that you get in quadrant 4 are negative angles, right? From negative 90 to 0, from negative pi over 2 to 0, over here you have negative angles. And now let's look at tangent. Again, we need to pick two quadrants such that no two angles have same tangent value. So we're going to be using quadrants 1 and 4 again, similar to sine. And the way we're going to describe this interval is from negative pi over 2 to pi over 2 again. The difference is that we're not going to include the endpoints compared to the domain restriction for sine. And that's due to the fact that tangent is undefined at negative pi over 2 and pi over 2. Once again, I'm going to remind you that in quadrant 4, angles are negative. And specifically, the values that we're going to be using are negative pi over 3, negative pi over 4, negative pi over 6. Well, and then you reach 0, right? Okay, so these are the domain restrictions for cosine, sine, and tangent. The cosine, sine, and tangent functions are one-to-one on these intervals. And that means that we can obtain their inverses. Let's see how that works. We're going to use cosine function again as our example. So we already restricted its domain, so it means that inputs are going to be angle measures between 0 and pi. Remember quadrant 1 and 2. So let's use pi over 4 again. It definitely comes from this interval. The corresponding output is radical 2 over 2. We already know that. Input, output. Now let's obtain an inverse function. Cosine inverse. Remember, the inverse function is the one where inputs and outputs are switched compared to the original function. So that means that radical 2 over 2 is going to be input. And pi over 4 is going to be output for the inverse function. It's going to take some real number, well, radical 2 over 2, and produce angle measure pi over 4. And here's the notation for cosine inverse function. It's cosine with negative 1 right next to it. That looks like a power, but not a power. It's the notation for the inverse function. And here's one very important note. Since the original cosine function has restricted domain, and we say it here, inputs are angle measures between 0 and pi. Once we obtain cosine inverse function and all inputs of cosine become outputs of cosine inverse, now we have to say that outputs are going to be angle measures only between 0 and pi. Inverse cosine function cannot produce any other angles. So it means that while a regular trigonometric function has to have restricted domain, inverse trigonometric function is going to have restricted range, restricted outputs. Let's look at other inverse trigonometric functions. We already know that inverse cosine function is written this way. However, there is one more way to write inverse cosine function, and here it is. We can write arc cos of x, arc cosine of x. They have exactly the same meaning, so there is no difference which notation you use. The result is going to be exactly the same. And in a similar way, inverse sine function is going to have this notation, either use -1 or write arc sine. And here's the tangent inverse function. In the next video, we're going to look at the examples how to find values of the inverse trigonometric functions.